Welcome to class, everyone. Today, we are diving into the absolutely fascinating world of redox chemistry. But we aren't just going to look at it as a dry list of abstract equations on a whiteboard. Nope. Instead, we're going to treat electrons as the ultimate currency of the universe. I'm your host, and in this explainer, we'll explore this invisible, microscopic economy where atoms are constantly trading, hoarding, and sharing their wealth. It's a system that drives literally everything around us, from the rust on an old bicycle to the cutting-edge batteries powering our future. Here is the syllabus for today's masterclass. 1. Beyond the oxygen myth. 2. Rules of electron bookkeeping. 3. Categorizing the chemical economy. 4. Visualizing the electron transfer. 5. Agents and common student traps. And finally, 6. Redox powering our world. All right, Section 1. Beyond the oxygen myth, from oxygen addition to electron transfer. Let's start things off by clearing up a historical misconception. This is something that trips up so many of my undergrads when they first study chemical reactions, so we really need to jump over this conceptual hurdle right away. Originally, chemists thought oxidation was strictly about, oxygen. And honestly, that makes total sense, right? Oxygen makes up about 20% of our atmosphere, so elements are constantly combining with it. When magnesium burns, it adds oxygen to become magnesium oxide. Classical oxidation. But as our scientific understanding evolved, chemists started noticing similar reactions happening with other electronegative elements, like fluorine or chlorine, without a single oxygen atom in sight. So we realized we had to broaden our definition. Modern oxidation isn't just about adding oxygen anymore. It's about the complete spending or loss of electron capital. It's a comprehensive electron transfer model. Simply put, oxidation is the loss of electrons and reduction is the gain. Moving on to Section 2, Rules of Electron Bookkeeping, Assigning Oxidation Numbers. Now, to track all this chemical currency, especially inside covalent bonds, where electrons just kind of shift slightly toward one atom rather than completely transferring, we use a financial accounting system. We call this system oxidation numbers. Think of an oxidation number as assigning a net worth to each atom. Now, in covalent bonds, we know atoms share electrons, right? But for the sake of our bookkeeping, we just pretend there's a complete transfer of electrons to the more electronegative atom. It's an assumption made purely for tracking purposes, but it brilliantly illustrates the shifts in electron density and gives us a beautifully simple way to track these redox reactions. So whether you're analyzing simple table salt or some wildly complex polyatomic ion, you absolutely must follow these 6 golden steps to balance the accounting ledger. Rule 1. Free elements, like pure oxygen or solid sodium, always equal 0. Rule 2. Monoatomic ions just equal their charge. Rule 3. Oxygen is almost always -2, except in peroxides. Rule 4. Hydrogen is +1, except when it's hanging out with metals. Rule 5. Halogens are usually -1. And Rule 6, your ultimate audit. The sum of all oxidation numbers has to perfectly equal the total molecular or ionic charge. Now, check out this number, 2.5. Sometimes our bookkeeping results in a fractional average net worth. For example, in the tetrathionate ion, the average oxidation number for sulfur calculates to exactly 2.5. My students always ask me, Professor, how on earth can an atom transfer half an electron? Well, actually, scratch that. It can't. The fractional number is totally an illusion of the average. Structurally, the 4 individual sulfur atoms have whole number states of +5, 0, 0, and +5. The reality of the electron economy is always in whole numbers. Let's dive into Section 3, Categorizing the Chemical Economy, 4 types of redox transactions. Now that we know how to track the money, let's look at the 4 main types of market transactions in our chemical economy. Because just like in global finance, there are different ways wealth gets distributed. These economic shifts range from simple corporate mergers to massive, complex restructurings. Combination reactions, those are like mergers, elemental carbon and oxygen combining to form carbon dioxide. Decomposition is the exact opposite, breaking down a compound like water into hydrogen and oxygen. Displacement is essentially a hostile takeover, where a more reactive element displaces a weaker one. And disproportionation? Oh, that's a fascinating scenario. That's where a single element in an intermediate state simultaneously earns and loses capital, oxidizing and reducing at the exact same time. Hydrogen peroxide decomposing into water and oxygen is a classic, real-world example of this. Section 4. Visualizing the electron transfer, a metallic displacement storyboard. Let's slow things down a bit and look closely at a specific displacement transaction. placing a solid zinc strip into an aqueous copper nitrate solution. Over the course of an hour, you can physically watch the economy in action. It's like a tiny movie playing out in a beaker. At 0 minutes, you have this solid silver-colored zinc strip sitting in a bright blue copper ion solution. As time passes, the zinc actively spends its electrons. It oxidizes, dissolving into aqueous zinc ions. You'll actually see the blue color of the solution start to fade away as the copper ions cash in those electrons, reducing from an aqueous state to coat the zinc strip as a solid reddish copper metal. It is a direct, completely spontaneous transfer of wealth. But you might be wondering, why does the zinc give its electrons to the copper and not the other way around? Well, not all metals are equally generous philanthropists. This activity series basically gives us a credit rating for metals. As you can see, zinc has a much higher tendency to release electrons than copper does. It's a stronger reducing agent. Copper, in turn, is more generous than silver. And let me tell you, this natural competition for electrons is the foundational principle behind how we design every battery you've ever used. Section 5, Agents and Common Student Traps. Identifying oxidizing and reducing agents. Okay, let's hit pause right here because we are approaching a major conceptual hurdle. A super common trap my students fall into is confusing who is doing the spending and who is collecting the debt in these transactions when we start talking about agents. Take a second to really think about this one. If a substance loses electrons and is oxidized, is it the oxidizing agent or the reducing agent? Got your answer? This naming convention feels totally counterintuitive at first glance, and honestly, it leads to a ton of mixed-up exam answers. Let's definitively break down exactly how we label these agents once and for all. Here is the trick I teach my classes. An agent is named for what it does to the other guy. The reducing agent? That's the philanthropist. By generously donating its electron capital, it forces the other substance to be reduced. In doing so, the philanthropist itself gets oxidized. Conversely, the oxidizing agent is the debt collector. It aggressively accepts or strips electrons from another substance, causing that substance to be oxidized. By collecting those electrons, the debt collector itself is reduced. So, to sum it up, the substance oxidized is the reducing agent, and the substance reduced is the oxidizing agent. Got it? Section 6, Redox Powering Our World. Industrial and environmental impacts. So let's zoom out. Why does all this invisible electron accounting actually matter outside the four walls of this lecture hall? Why should we care about which atom is the debt collector and which is the philanthropist? Because this very electron transfer drives massive global industries. We literally built our modern society on top of redox reactions. We use electrochemical processes to extract highly pure reactive metals from raw ores dug out of the earth. We manufacture vital, everyday chemicals like caustic soda. Every single time you start your car, use your smartphone, or burn fuel to heat your home, you are relying on a carefully engineered redox reaction. Even the slow, destructive rusting of a suspension bridge, that's just an uncontrolled redox process. And as the scientific literature points out, it's not just about industry. It's about our planet's future. The literature hits the nail on the head. Mastering these redox reactions is quite literally the foundational key to solving modern environmental challenges. The depletion of the ozone layer, that involves complex free radical redox chemistry. And the push for a pollution-free future relies entirely on our ability to manipulate these exact electron transfers. I want to leave you with this final provocative thought. As we look to replace fossil fuels with liquid hydrogen, and as we try to build massive battery grids to store solar and wind power, we are essentially trying to become master accountants of the electron economy. As you continue your studies, consider how you might use these exact rules of electron transfer, this fundamental flow of microscopic currency, to engineer the green fuels and sustainable batteries of our future. Thank you so much for joining me in this explainer today. Class dismissed.